This module is the first module we're going to have on the memory system. So this module 8 and 9 are about the memory system. This week we're just going to go over how they're set up. So obviously the memory system is very important, like right next to the CPU, and importance for a computer. And we store instructions and data in a memory system. So we saw that with load word and store word, exchange data with between the CPU and the memory system, and all the instructions that we load come from memory. So programs are kept in memory. So we want a large storage capacity because we want a lot of room for programs. And if we are running up against our capacity, we have to be very clever about how we do our programs so they take up less space. But if we have tons of capacity, that's not such a burden. Of course, we want it to be fast. We want speed, and in this week, speed means how fast can you get data to and from memory. And both of these things, capacity and speed, cause the cost, making them better makes the cost go up. So you have to balance all of these goals. And we're going to talk about caching, which makes it seem like things are faster. So caching helps with speed, and virtual memory helps with capacity, makes it seem like our memory is bigger. So memory can be RAM, random access memory, or ROM, read-only. So it can be read but not changed, and RAM can be changed and updated. So when we access memory, it's a read or a write. And if we're accessing memory, it's given an address. So where we're going to get that from the memory is going to be in the form of an address. And we're going to talk about how many bits are needed to address make an address in memory. So the capacity is measured in units of 8-bit bytes, and an address is going to be for a particular byte. So we're going to mostly talk about byte addressable. So if we can address a byte, and we measure it in bytes, so if we have 64 bytes of memory, which is obviously very small, there's going to be 64 memory addresses. So if there's 64 addresses, 64 is 2 to the 6th. So we're going to use 6 bits. So each address is going to be 6 bits. If we were to had to give an address that's between 0 and 63, which would be 64 addresses, and that address value between 0 and 63 is going to have to be in binary. Our addresses are in binary. It's going to take 6 bits. So we're going to say that address is 6 bits long. So we have an access, a location. We're going to get copy, read will get data from memory, and write will place data in memory. So just like our processor, so we've been talking mostly about the processor so far, just like our processor operates on a clock signal, so does memory. So on the clock signal, on the beginning of a cycle, we're going to send data to memory, and at the end of the clock cycle, it will be in memory. So they both have the clock. So this is going to be a bit that says whether we're writing. So that's going to be a 0 or a 1 control signal to let it know whether it's a write or a read. This is going to be the address that in memory that we're interested in. If we're writing, the data will come across a bus. If we're reading, the data will go from memory to the processor. So I talked earlier that most systems are byte addressable, so you can access an individual byte. But the actual transfer size might be more than a byte, so we'll talk about that. In MIPS, we're going to actually transfer a word with every transfer, and that's 4 bytes. So we address a byte, we say we want to go to this address, but we're actually getting 4. So maybe if this is 0, 1, 2, and 3 are the addresses, we would say, give me the word at address 0. And it'll give me the word at address 0 and the next 3. And then we can also, so if we're, again, getting a whole word, we're going to have to get it on a multiple of 4. We're going to have to give it a multiple of 4 as an address. And I talked about this earlier, the amount of physical memory dictates the number of address bits. So again, if we had 128 bytes of memory, that would mean 128 different addresses. So that's 2 to the 7th, so 7 bits would be in the address, because the address is given in binary. And again, the width of the pathway dictates the number of bytes in a transfer. So if our bus has a width of 4 bytes, that's what's going to be transferred. So we'll talk about the width. And most of the time you can only do one read or write at a time. So this is interesting. If our address register is only 32 bits wide, which it is in MIPS, that means our maximum address is going to be 2 to the 32 minus 1. So even if our memory is larger than that, we actually would put it into blocks of the size of 2 to the 32. In MIPS, our registers and our words will be 4 bytes. So our addresses are 32 bits. So a read or a write is going to be in a cycle, and the cycle time is going to be the same for the CPU and the memory. And the access time is actually the time between the request and the return of data. So that doesn't include the setup and recovery time. And again, we have 2 buses. And with the memory, there's an address bus and the data. And so that's the bit that's 44 bytes in MIPS. And the address bus is also 32 bits, so that would also be 4 bytes because addresses are 4 bits. And then the request signal, like I said earlier, there's that 1, 0, whether we're reading or writing. So we're going to look at memory hierarchy, and it's, faster means more expensive. So as speed, expense goes up. So we arranged it in a hierarchy where we have some expensive fast and some slow. So we're going to have more of the cheaper stuff and less of the expensive stuff. And so the registers are going to be the fastest memory we have, and we're going to talk about cache. That'll be next. And it goes down from there. So here's an idea. We talked about the registers already. That's going to be the fastest. This is all the memory in our system. And so we're going to talk about caches and then the main memory. And then hard drives are going to be here, and it goes down from there. The expense, the speed, more costly, faster access time. So now we're going to look at the difference between little endian and big endian, starting with big endian. So remember, when we access memory, we're going to get 4 bytes, but we're going to give it the address of a byte. So if we give it address 200, say that's what I want, I'm going to get 200, 201, 202, and 203. So in a big endian, how is data stored? So in big endian, the most significant bits are stored in the lowest address. So kind of left and left. Okay, so this would be 200, 201, 202, and 203. Little endian reverses that. And so when we say we're going to get 200 again, we say give me the word that starts at 200. Little endian is going to put the least significant bits in the first byte. So that's what this would look like. So there's 200, 201, 202, 203. So up to now we've studied combinational logic, where there's an input, send it through the circuit. We studied some gates and combinations of gates that when it runs through here, it comes with an output state. And this happens on clock. So at a clock, we take the states and put them in. At the end of the clock cycle, it has a new state. Combinational logic depends only on the current inputs, not on the history. But memory is going to have a memory of history. So it's going to depend on the history of the inputs. And so it's going to save history. So we're going to learn a little bit about sequential logic. So memory is all about storing values and storing sets of ones and zeros. And so we're going to remember down to individual bits, whether bits are on or off. So for each bit, we have to have some way to store whether it's on or off. And one of those ways is called an SR latch. So the output is Q and not Q. So if Q is true, then that's a 1 stored in that bit. And if it's not Q, it's a 0 stored in that bit. And the inputs are these S and R, set and reset. And these are going to determine whether we remember or how we remember the Q and the not Q. So this is how we permanently store a value in memory, is with a little circuit like this. So as we start out, in the beginning, S and R are 0. And if we send in a message that says set, it's going to set this Q to be 1, or so now the bit is set. And it'll stay that way, as we'll see. Because once Q was 1, even if we change this S back to 0, so now we're sending, even if we send this back to 0, this output here is still going to be 0. So we're going to have 2 zeros into this gate, and it's NOR, so the output's going to be 1. And so here we're having a 1 and a 0 coming in, so the NOR will be 0. So this is stable. So even if we set S back to 0, it remembers that Q is 1. To change this Q value from 1 to 0, we would have to put in reset. So if we send a 1 here, the output is going to be 0. And so then we'll have 2 zeros coming in here, and the output will be 1. And so that'll be stable. So we set the reset signal, we'll set this to 0, and it'll stay that way. Even if we set R back to 0, it's going to continue. So set turns the bit on, and it stays that way. Reset turns it off, and it stays that way until you hit set again. So this is sequential logic, and instead of a truth table, we have a characteristic table. So once we have inputs, we're saying it's going to be an input at time t and an output at time t plus 1. So if they're both 0, it's just going to be continue with whatever it was. If you hit the reset, it's going to go to 0. If you hit the set, it's going to go to 1. And if they're both 1, I don't know how you did that, and we don't really know. It's undefined. So the latch is what we just saw, and the difference between a latch and a flip-flop is when it changes. So if the clock is asserted when you set the value, if the clock is already in the up, S will turn to 1. So it's dependent on when you flip this. Flip-flop is not, instead of being dependent on when you flip this, it's when the clock edge. So the clock edge controls when it gets set, and in this one, just the turning as asserting S depends is when it gets flipped. It's a subtle difference. So a D gate has only one input. So the SR had 2, D has 1, and the clock. So D equals 1 is the same as S equals 1, and D equals 0 is the same as R equals 1. And here's the idea of a D latch. So remember, a latch changes with the clock. So here we turn D on, and as soon as the clock asserts, it comes on. And then the D goes down, and as soon as the clock asserts again, the output goes down. So I added another example to understand latch, where the output goes with the input as long as the clock's asserted while it happens. So to kind of distinguish this from flip-flop. So here it goes, the signal goes up, the clock is asserted, so Q goes up with it. And here the signal goes down, the clock is asserted at that time, so the signal goes down with it. So here's a D flip-flop on the falling edge of the clock. So here on the falling edge of the clock, the output gets asserted because D is asserted. And then at the falling edge of the clock, it goes down because D is down. So it changes with the clock. So with RAM, we're going to store bits, and it's stored as a charge on a capacitor. So if a word line is asserted, which will show what that is, so that's saying I want a certain word, so it's going to activate a word line. Each bit line that is active, oops, I wonder what I did. Each bit line that is active, if there's a charge, it'll represent a 1. So that's how we're going to store memory, is in these bit lines, and then when we want a piece of memory, we activate a word line. So we'll see kind of how that works. So as discussed earlier, we're going to send memory to and from the CPU over several buses. This is the control signal we talked about. Am I reading or writing? This is the address I want. And this is the data that's going either to memory or from memory. And then we have it connected first to ROM, closest to the CPU, then RAM, and then maybe bulk storage like hard drive. But our bus is just a set of wires, and data goes over the bus. As we organize memory, it's going to have a width, and the width would be the number of number of bits in a word is the width, and a word is what would be transferred every time memory is transferred is a word. So that would be the width. The word is the width. We look at it this way. And the number of words in memory is its height or depth. So we're going to have two dimensions, the width. The size of a word is the width, or the size of what's transferred, and the depth, how many words fit in the memory. So the previous showed a memory array, and it had 8 rows. So to describe 8 rows, we need 3 bits. So here an address would be 3 bits long. To describe those, any of those 8 rows would be described with an address. And the array size is going to be n is the number of bits in the address. And m is the number of bits in the word. So the size would be 2 to the m, n times m. Here's an example where the width is 3 bits, and there are 4 rows. So the number of words is 4, so that the address takes 2 bits, and the word size is 3 bits. So to activate a certain word to send it back, you would activate a word line. So we saw that the words were in a row. So there'd be a signal that would go into that word line saying, turn it on, this is what I want. And then there's going to be a bit line for every bit in it. And if it's on, it'll return a, if the stored bit is 0, that bit line will return a 0. If the stored bit is 1, and so on. So when you turn on a word line, it's saying, give me everything that's in that row. Turn on the bit lines and return what's in there. If the word line isn't turned on, nothing is returned. Even though there's something stored in there, nothing's returned. So here's a picture of the idea of a whole memory put together. So we're going to come in with an address. It's going to be 2 bits. And so those 2 bits can get turned into 4 addresses. And so we're going to have to take an input of 2 and turn it into a decoder that gives us a choice of 1 of 4. So we need a 2 to 4 decoder. And then when we get our choice, say it's 1, 0, this word line will be active. And so each of these bit lines will be active. So 1, 0, 0 will be sent along. So here's how it looks. So the data would be a 1 or a 0. The selector would be if that word line is chosen. And so the output would come as a result of the actual data and whether it's selected. So if you have a larger memory, like maybe more memory than, more rows than 2 to the 32, you could put multiple chips together and then have a chip select signal to say which chip you're going to choose. And again, you have the read-write control signal, an address. So if you have a memory chip where there are 2 to the 21 words, so that would be 2 times 2 to the 20th, and 2 to the 20th is a megabyte, so that would be 2 megabytes. So the address is 21 bits. And then we're passing in, each word is 16 bits. And then this would be the chip select signal, whether we're reading or writing. So we'd pass in 21 bits. Then we would have to turn that into a choice of 2 to the 21 words. That's a lot. And then we would have 16 bits come out. So there's 2 to the 21 rows. So we're going to have to do a 21 to 2 to the 21 decoder. That's pretty big. So we're going to pass in 21 bits and get a choice of 1 out of 2 to the 21 possibilities. So, but that's quite a large decoder. So here's a way to do it with two smaller decoders. So we take the 21-bit address, I guess it would be a 22-bit address. Maybe that should be 20. Anyway, so you take the top 12 bits and say, okay, out of the top 12 bits, there's going to be 4096 choices. So here's a chip with 4096 rows in it. And then each row will actually have 2 to the 10 choices of data in it. So the lower bits will tell us which of the 2 to the 10 bits in this row will be chosen. So the top decoder chooses a row, and this lower one will choose which bit out of the bottom, according to the bottom 10 bits, which bit in this row will get chosen. And then there should be 16 outputs. If it's according to the last one, they only show 8. But this is splitting it up into 2 pieces. We've talked briefly about DRAM. Double data RAM stands for double data rate RAM. And it transfers data on both the rising and the falling clock edge, so it transfers double the amount of data. So we also have memory interleaving here. A single memory module can perform one read or write at a time. And interleaving refers to how consecutive locations are distributed. So if you were going to read 2 in a row from an array, maybe you want to be able to get that quickly. So if we're going to have multiple modules, we can split it into modules, and perhaps we could read one module, like 2 modules at the same time if we had, the right communication. So how would we decide what goes into what module? So high order interleaving has consecutive locations in the same module. So the upper bits are the module number and the lower bits are the offset. And so if you have consecutive locations, it's going to be from the same module, so it has to be sequential. So here's an example where each module has 8 items in it, or 8 addresses. So address 0, 1, 2, and so on would be in module 1, and then the next 8 would be here. So that's high order interleaving. So another way is low order interleaving, where the lower part of the address indicates the module number, and then so consecutive addresses are in different modules. And here's an example where 0, 1, 2, 3. So if you're doing an array and you had the communication to do it, you could get several at a time from an array. So we've seen this before. This is our register file. We have register numbers, read and write. If we're reading 2 registers, we have 2 ports for that. A port for a write register, the data we want to write to the register file, the data we've read, and the control signal. And again, we have this 5-bit comes in and 5 bits, and this is 32 bits, 32 bits, and 32 bits. And this is what it might look like. So the read register is a choice between 0 and 32, as is this. And then coming out of this mux, based on the choice, would be the read and write data. Then if we're writing in the control signal, so if the control signal is 1 and we figure out which register number, so if both are 1, we're going to write to here. So this is going to be saying yes, write, and then it'll write the data.